Welcome viewers, in this video we will see the details about maximum power transfer theorem. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic maximum power transfer theorem. We'll see the case 1. Purely resistive circuit and the load resistance is variable. The circuit is contain only resistance and the load also resistance, that is variable. The statement of the maximum power transfer theorem is maximum power will be delivered from a voltage source to a load when the load resistance is equal to the internal resistance of the source. This is the statement given. Maximum power will be delivered from the voltage source to the load when the load resistance is equal to the internal resistance, right? If the load resistance is equal to the circuit resistance, the maximum power will be delivered from voltage source to the load. That is the statement given. Now consider this circuit. We will verify this statement. Consider a voltage source of generated voltage Vg and internal resistance Rg connected to a load RL as shown in the diagram. Right? So we have the voltage source Vg. This is the load resistance, load current, the terminal AB. The load resistance is marked as terminal AB. The Rg is the internal resistance. So based on the maximum power transfer theorem, this Rg is equal to RL. Both are equal. If it is both are equal, then this voltage source will deliver maximum power to the load. That is the statement given, right? So we have voltage source, internal resistance, load resistance, load current. This load resistance is marked as terminal AB. Now we will go for the further derivation to verify how the maximum power is delivered to the load. When the power transfer to the load is maximum, RL equal to Rg. That is the condition given. So RL equal to Rg when the maximum power is delivered to the load. At this condition, the total resistance is Rg plus RL. So we'll take it as 2RL. Both are equal. So we'll take it as RL equal to Rg equal to RL. So the RL plus RL, 2RL. So based on that, the load current IL equal to V by R. Voltage is Vg, voltage source. The resistance is 2RL. So IL equal to Vg divided by 2RL, right? So from the condition, we start from the condition maximum power transfer theorem. When the power is transferred to the load is maximum, the load resistance equal to system resistance, internal resistance. So at this condition, the total resistance is Rg plus RL, so it becomes 2RL. From that we can calculate the load current IL equal to Vg by 2RL. Vg is the voltage source available in the circuit divided by total resistance 2RL. From that we can find the power delivered to the RL. The formula is I square RL. There are three formula available. V into I square R, V square by R. In that we are using this I square R, IL square into RL. So IL square already calculated Vg by 2RL. So Vg by 2RL square into RL. So while squaring it is Vg square divided by 4RL square into RL. Right? One RL got cancelled. Here RL available, here RL square is available. So one term got cancelled. So finally we have Vg square divided by 4RL. Power delivered to the RL is Vg square divided by 4RL. So after implementing the condition, after simplification, we got this equation, power delivered to the load. So in the maximum power transfer theorem, the condition is given means we can use this formula for maximum power delivered to the load. Vg square divided by 4RL. I will go for the further details. So based on that, the maximum power delivered to the load. So power delivered to the load, the condition is given maximum power will be delivered to the load. So that it become a P max. So we calculated power delivered to the load based on the maximum power transfer theorem. That power delivered is a maximum power because it is condition is given. When RL equal to Rg, the maximum power will be delivered. So P max equal to Vg square divided by 4RL. So this is the formula to find the maximum power delivered to the load when the condition is given in the problem itself, we can use this formula. So the second case, the reactance is present. Previously we have only resistance and load resistance, and the reactance can be independently varied. The load is contained resistance, but the system contain, the circuit contain the reactance. So what is the statement given? Maximum power will be delivered from a voltage source to the load when the load impedance is a complex conjugate of the source impedance. In previous case, the internal resistance is equal to load resistance, but here the reactance available, so we have the complex conjugate. The complex number will be there, the real term and imaginary term, because of reactance. It may be the capacitive reactance or inductive reactance. So that the same condition is here also same. Power delivered will be, maximum power will be delivered from the voltage source to the load. Only the condition is load impedance is complex conjugate of the source impedance. Both are complex conjugate. Complex conjugate means A plus JB means the complex conjugate will be A minus JB, right? The load impedance and source impedance are complex conjugated. Now we'll see the further derivation, further details about the case 2. So ZZ, the internal impedance of the source, we can take RG plus JXZ, right? Previously we have only resistance, now we have impedance also, right? So RG plus JXG. Then ZL is RL plus JXL, load reactance but not inductive reactance, right? So this is the system internal impedance, this is the load reactance. So based on the condition, both are complex conjugate. According to the maximum power transfer theorem, ZL equal to complex conjugate of ZG, that is RG minus JXG, right? So ZL equal to ZG, but it is complex conjugated. Previous case what we have, RG equal to RL, right? Load resistance equal to system, the internal resistance. Here the load impedance equal to internal impedance, but it is complex conjugated, RG minus JXC, right? Okay. Then we'll go to the third case. Reactance present, but only the magnitude of the load impedance can be varied, right? Only the magnitude is varied. Here also reactance is present. Now we'll see the statement. What is the statement of this? Maximum power is delivered from a voltage source of a load when magnitude of load impedance is equal to magnitude of source impedance. Previously we have complex conjugate. Now here only concentrating the magnitude. So magnitude of load impedance equal to magnitude of source impedance, right? Only we have concentrated the magnitude. So let theta be the angle of the load impedance, the angle of the load impedance, so that ZL equal to ZL angle theta, that is ZL cos theta plus JZL sin theta. This is the polar form, this is the rectangular form. Polar form we have magnitude and angle. Rectangular form we have real number plus imaginary number, real term plus imaginary term, right? So P equal to Vg square ZL cos theta divided by Rg plus ZL cos theta square plus Xg plus ZL sin theta square. So this is based on the previously we have Vg square divided by 4RL. Based on that we obtain this formula, right? P equal to this Vg by R. We concentrated only the magnitude, right? So this is the resistive term, reactive term. So the maximum power, for maximum power transfer, dP divided by dZL equal to 0, right? In order to get the maximum condition for maximum power, this equation is differentiated with respect to ZL, because ZL is a variable, right? Load impedance. So that is equal to 0. By equating 0, we are able to get the condition for maximum power transfer. Now we'll see the condition. So using this condition and simplifying the above equation, the simplification is not given, directly the expression is given. Rg square plus Xg square equal to magnitude of ZL square. That is magnitude of ZG equal to magnitude of ZL, right? So the derivation is not given, directly we have the expression is given. So the third case is nothing but magnitude. Magnitude of the internal impedance equal to magnitude of the load impedance. Both are equal, right? So we have further some more details are available. It may be mentioned that this condition hold good for a transformer where the turns ratio is varied for a maximum power transfer theorem. So it can applicable for the transformer also, right? So we will go for some more details. If the source impedance is purely resistive and load impedance consists of variable RL and fixed reactance X, then the maximum power transfer theorem. Maximum power transfer is RL square equal to RG square plus X square, right? The source having the only impedance and load impedance consists of RL as well as reactance. If all these things are available, then it is RL square equal to RG square plus X square, right? RL square is the load resistance. RG is the internal resistance. X is the variable reactance that consists of the variable reactance X. If the load impedance is purely resistive equal to RL, but the source impedance consists of both resistive and reactance, then the power delivered to the load can be maximum by varying RL. The power transfer theorem is maximum when the power transfer is maximum when RL square equal to RG square plus X square. Otherwise, RL equal to ZZ, right? So only RL is contained. Resistance contain only RL, but source contain resistance and reactance. In that case, what is given? That we can vary the RL value so that we'll make the both are equal and we can get the maximum power transfer. So that is RL square equal to RG square plus XG square. So these two is constant, but we can vary this. By varying this, we will make both are equal. Under that condition, RL equal to magnitude of ZZ, right? We'll go for further conditions. When conditions for maximum power transfer to the load are satisfied, the load is said to be matched to the source. That is, load and system source are equal. For solving any problem on maximum power transfer theorem, get the Thevenin equivalent for the given circuit, right? So while doing all maximum power transfer theorem, the first step is we need to get the Thevenin equivalent circuit. What is Thevenin equivalent circuit? Voltage source connected in series with the impedance, Thevenin impedance, right? VTH connected in series with RTH. RTH is nothing but system impedance, the internal impedance. So that the maximum power transfer theorem is very simple. This internal impedance is equal to load impedance. So if we got the Thevenin equivalent, it is a simplified circuit contain only voltage source and one internal resistance. So we need that internal resistance. Internal resistance equal to load resistance. So that the fully circuit will be, the complicated circuit will be simplified after getting the equivalent, the Thevenin equivalent circuit. From that we can easily identify the system internal resistance that is equal to load resistance. So in this video we discuss about the maximum power transfer theorem. The condition for maximum power transfer theorem. Finally, we got the maximum power delivered to the load, Vg square divided by 4RL. That formula can be used when the power delivery is maximum. We also discussed the reactive cases, case 2 and case 3, variable or magnitude. In that, finally, the important thing is we need to find the Thevenin equivalent. Before going to proceeding, we need to find Thevenin equivalent. From that, we can easily calculate the maximum power transfer to the load. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.